Okay, so for my non-constant forces video reassessment, I chose a homework problem from the list of homework problems that you assigned us on the blog. It's a problem from the book, problem 2.8. And digging right in, all right, so the problem reads, a mass m has velocity v naught at time t equals 0 and coast along the x-axis in a medium where the drag force is f of v is equal to negative cv to the 3/2 power. Use the method of problem 2.7 to find v in terms of the time and the other given parameters. At what time, if any, will it come to rest? All right, so just clearing up something here. It says use the method of problem 2.7. That's kind of some background information. Basically, the problem 2.7 just kind of introduced how we can use, and it's also talked about throughout the chapter, but it just basically introduces how we can use separation of variables to basically turn the problem into an integral. You know what I'm saying? To use Newton's second law, Newton's equation of motion. Newton's second law, which is the equation of motion, to basically we can integrate and we can use separation of variables and integrate to solve for v as a function of time, basically v of t. And we also discussed that in class, but I'm just kind of show it here. So, all right. So basically, just starting off. All right. So basically, yeah, I already cleared up basically what it was saying, where it says the methods of problem 2.7. Basically, that's just separation of variables and integration. All right. So here, start off with just kind of getting the visual. So here we have our mass is coasting along the x-axis. It starts off at t0 and it has initial velocity v naught in the x direction, but it's subject to a drag force, which is here. F of v is equal to negative cv to the 3/2, and c is just a constant, and v is just saying that the drag force depends on the mass's velocity. It's dependent the force is dependent on the velocity, so therefore that makes it a non-constant force. So basically, just like the problem asks, I'm trying to find velocity in terms of time and the other given parameters, which is v naught, m, and yeah, those are the other given parameters, basically just given. All right, so I start off with my free body diagram, and like I said, the only force, the force of gravity is canceled out by the normal force because it says that it's coasting along, so therefore it shows that it is something canceling out the force of gravity. All right, so I start off right here. My drag force is equal to negative CV to the 3/2. Newton's second law tells us that F is equal to MA. I can rewrite MA as V dot, which is dV dt. Basically, that's going to help along when I use separation of variables. All right, so F of V, we also know earlier as the problem discussed that the only force that the object was subject to was the drag force. It's already in motion, but the only force that it's subject to is the drag force, which is negative CV to the 3/2 power. So therefore, I'll replace my forces, F of V, by negative CV to the 3/2 power. And then we know basically mass times acceleration on the right side, because we know that the force is equal to mass times acceleration of our object. Okay, so basically just switching the equation around. So therefore I have dv dt is equal to m times m is equal to negative cv, and that's once again just force is equal to mass times acceleration. So here, this is where we bring in basically a differential equations technique, which is separation of variables, in order to solve this differential equation. So therefore I multiply both sides by dt to get this dt over here in with these variables, and I move my v over here to get it in terms of dv. You get what I'm saying? We want to get the like terms together, so we want to get dv. That's part of using the separation of variables technique. So basically, I just get dv over here. I move my v terms over here. I get this in terms of dt, and then I integrate. You get what I'm saying? Just basically, I'm trying to solve. I'm trying to get this in terms of v. I'm trying to get this in terms of t. And just like the problem asked in the beginning, I'm trying to find velocity in terms of t. So let's kind of speed this up because I'm getting close to 5 minutes. Basically just integrating. My limits of integration is v naught to v, because we already said that the particle starts with v naught velocity, and we trying to figure out v. We trying to find out what's its velocity v. So therefore, I changed this v in the integral to v prime just to not get those confused. And then just moving along, here go my integration, integrating. This is what I get. So I end up getting basically v, and then I'm getting v in terms of t and all the other given parameters we were given initially, which is c, m, v naught. So basically I get v is equal to 1 over ct times 2m plus 1 over the square root of v naught squared. And the second part of the problem basically asked at what time does v equal, at what time, if any, will it come to rest? So basically we just trying to see at what time will v equal to 0. And basically as we see, since it's 1 over this right here, v would never really go to 0, but it'll approach 0. So v approaches 0 as t approaches infinity, which makes sense because as it's moving along, since the drag force is dependent upon the velocity, as the particle, basically as our mass is moving along the x-axis, basically as the further and further it goes along and the more and more that it slows down, the less and less the drag force is going to be. So it'll never really approach 0. I mean, it'll never really get to 0, but as time goes along further and further, our velocity will approach 0. And basically that's it.